let's take a look at a few definitions. When we're taking a number and using it to describe the population, that is an example of a parameter. Now, a parameter is going to be a fixed number. Usually we won't know this number because it would be almost impossible for us to know the values for every individual in a population. But could we find that? Could we collect that data? We could know the exact value of that parameter. Now, a statistic is going to be a number that describes a sample. Now, parameters and statistics can often be describing the same thing, but a statistic is going to come from a sample and a parameter is going to come from the population. Because statistics are coming from samples, which are small groups from the population, then the value of the statistic can be known because it's going to be from a small group, but it also can change from sample to sample. One of the big ideas in statistics is taking a statistic in order to estimate some unknown parameter. We're going to look today at this specific parameter and a statistic. We're going to be talking about proportions for this lesson. So p hat is going to be the notation that we use for the sample proportion. This would be a statistic, and this is going to quantify the proportion of people or individuals who have some trait or some opinion of interest. P is what we're going to use to label the population proportion. This will be a parameter because we're interested in describing the entire population. So for example, if we had a Columbia-based health club wanting to estimate the proportion of Columbia residents who enjoy running, P would be the proportion of all Columbia residents who enjoy running. Instead of trying to ask every Columbia resident, we'll just take a simple random sample of size 100. P hat is going to represent the proportion of residents in the sample who enjoy running. So let's say that we found 17 who said that they enjoyed running. To calculate the sample proportion, you take the number that have the trait that we're interested in and divide by the sample size. So in this case, P hat would be 17 divided by 100, which in your calculator you'll get 0.17, and you can convert that to a percent, and it would be 17%. Now, if we took another sample of size 100, we probably would get a different number who said that they enjoyed running. In this case, we get 22, and the p hat for this sample would be 22 over 100, which is 0.22 or 22%. So we noticed here that even though our samples were coming from the same population, the sample proportions were different. So are statistics from different samples but drawn from the same population going to be exactly the same? Well, usually not. There's usually going to be some variation from sample to sample. Also, we should think about whether or not the statistic from a sample is going to exactly match the population parameter. Well, when we think about this, it's also pretty unlikely that our sample gives us the exact same value as the entire population. So the fact that our statistics will not be the same from sample to sample is called sampling variability. And that just is a way of us explaining that we understand that all samples are going to be a little bit different from each other. But what we hope is that as long as we use good sampling schemes, when we are estimating the population parameter, we'll do it fairly well when we take our one shot at estimating. Our sample statistic is going to provide us the basis from which we create an estimate for a population parameter. And it's not always perfect, but hopefully we'll get pretty close. We already talked about bias, but here we're going to see this in context of estimation. So here, bias is going to be the consistent repeated deviation of the statistic from the parameter in the same direction when we take many samples. So if you have an example of something where your statistic is constantly overestimating or constantly underestimating in that same direction, then that's going to be bias. We want to avoid bias. But variability is describing how spread out the values of the statistic are when we take many samples. And we expect to have some variability, But we don't want to have large variability because that means that the result of sampling is not repeatable. So a good sampling method should have small bias and small variability. You can think of bias and variability on a target here. So in the top left, letter A, this has large bias because it's very far away from the target. But it has small variability because all of the results are there in that same little region. Going to the right, letter B, this has small bias because most of the results are there close to the target. But they have a large variability because they are quite spread out. On the bottom left, letter C, this is an example of large bias and large variability because the results are clearly away from the target and they're still pretty spread out. But the bottom right is an example of small bias and small variability. We hit the target and we were usually pretty close to the other results. So what we're going to be doing in statistics is we're going to be thinking about how the samples vary from one sample to another. Even though we typically only take one sample, we need to understand what would happen if we were to take lots of samples. So imagine we have some population and the true population proportion is 0.5. If we go into that population and we take a simple random sample of 100, maybe we get a result like 0.56. If we go and take another sample of 100, maybe we'll get something different like 0.36. We can take a third sample, and this sample might provide a sample proportion of 0.61. Each one of these samples is going to be a little bit different. The graph on the right is showing you the results from lots of different samples. And you can see that most of the results are pretty close to the true population proportion of 0.5. Now, if we do the same idea, but this time take a larger sample. So this time we're going to take the sample size that was in the survey from the case study. Here, our sample size is 1,015. When you take simple random samples of this size from the population, here, each of your p-hats is going to be pretty close to the true population proportion. Notice here that almost all of the results were right there, close to 0.5, and the smallest result was still not that far below. It wasn't even as low as 0.45, and the largest results weren't even as large as 0.55. So here, when we had a larger sample size, we had a lot less variability. You also see that all of these samples, when graphed, we are centered around the true population parameter. And this is what's called being unbiased. This estimate, this p-hat, is going to be an unbiased estimate for the true population parameter. So when we are wanting to reduce bias, you should use random sampling. If you want to reduce variability, you should use a larger sample. So random sampling is going to provide you with an estimate that's close to the target, and a larger sample is going to produce a result that is very close in spread to the true target.